Welcome to Dynamical Systems and Fixed Points Part 2. If Part 1 wasn't enough, Part 2 maybe will be. I don't know. Last time, what we did was we learned about what dynamical systems were. We learned how they were expressed analytically and what fixed points were. We even learned a little bit about like the recursive relationship and what the requirements were for a fixed point to exist. So what I want to do this time is twofold. One, I want to expand on what we learned by working through another example, or two, or three. And then I want to expand upon what we've learned by looking at how the system behaves graphically rather than just analytically, right? So instead of just seeing numbers, you'll actually see graphs and go, oh, that's what it looks like. The idea would be if you see these and, see how it behaves and get the practice solving it analytically and graphically, you're going to be a dynamics whiz kid. And, well, enough BSing. Let's get started. Here's an example. Consider yt equals 1/3 yt minus 1, and we want to find that fixed point. So what's the first thing that we're going to do? Well, I'm going to set yt equals yt minus 1 equals y star. So every value of y is just equal to y star. So yt minus 1, if there's a yt minus 2, whatever. They're all equal to y star. And then I'm going to subtract 1/3 y star from both sides. I want to get y on one side. I want to get everything else on the other. So now I've got y star minus 1/3 y star equals 0. And I'm going to factor out that y star. So I'm going to get y star times 1 minus 1/3 equals 0. Now I could go ahead and evaluate that 1 minus 1/3 and get 2/3. But because reasons, I want to leave it as it is. So I'm going to divide both sides by 1 minus 1/3 to fully isolate y star. So I get y star equals 0 over 1 minus 1/3. Thus, y star equals 0 because, well, fractions and because 0. If there's no intercept, meaning if you have that form yt equals alpha naught plus alpha 1 yt minus 1, when alpha naught is equal to 0, the fixed point will be at 0. So if you ever just have yt equals alpha 1 yt minus 1, that fixed point guaranteed to be 0. It doesn't mean that there is no fixed point. It means the fixed point is at 0. If there is no fixed point, the end result looks very different. If that's not foreshadowing to the next example, I don't know what is. So let's see what happens when there is no fixed point. Well, there's two ways we can engineer it. Alpha 1 equal to 1, alpha 1 greater than 1. So let's do alpha 1 greater than 1 first. Now I'm doing it with an intercept here, really just to give you guys the full picture of what's going on. So now I've got yt plus 1 equals 3 plus 1.5 yt. Now, again, same process as before to find the fixed point. Yt plus 1 equals yt equals y star. So I now have y star equals 3 plus 1.5 y star. And I want to get y star on one side again. So I got y star minus 1.5 y star equals 3. I'm going to factor out that y star. So I get y star times 1 minus 1.5 equals 3. And I want to isolate that y star to get 3 over 1 minus 1.5, which gives me 3 divided by negative 0.5, which gives me negative 6. Okay, so, hey, that's a value, isn't it? So what gives? I thought you said there wouldn't be a fixed point or something. Well, you'd think there'd be a fixed point here. Maybe I should have said something earlier. I guess I just wanted to wait so you could really see what was going on here rather than just give you a bunch of rules up front. So that fixed point for y is supposed to be positive. If you have a negative value for that fixed point, there's no fixed point. We'll see why a little bit later. When you look at it graphically, it'll make a lot more sense. So if you have that negative value for the fixed point, there is no fixed point. Also, that intercept alpha naught has to be positive. Now there's more to it than just this, but well, all you really need to know for the class is just it needs to be positive. Plus, when we get to the graphing, again, you'll see why. So the fixed point is assumed to exist in positive space. What about when alpha 1 is, say, equal to 1? All right. Let's see what happens. Well, I now have yt equals 3 plus yt minus 1. Well, again, I set yt equals yt minus 1 equals y star. So I have y star equals 3 plus y star. Get y stars on one side. I get y star minus y star equals 3. I'm going to factor out that y star, have y star times 1 minus 1 equals 3. Divide both sides by 1 minus 1 to isolate y star. I get y star equals 3 over 1 minus 1. But then it's probably time to go ahead and evaluate what's in that denominator. Oh, shit. That's equal to 0. Ruh-roh, Raggy. We can't divide by 0 because rules. So if alpha 1 is equal to 1, that fixed point doesn't exist. And now you've seen how and why. Hooray, yippee, cool for us. Awesome. So what's the general form for the solution? Well, consider a general form of just yt equals alpha naught plus alpha 1 times yt minus 1. And we want to solve for a fixed point. So I do what we always do. We do yt equals yt minus 1 equals y star. So y star equals alpha naught plus alpha 1 times y star. And I'm going to subtract alpha 1 y star from both sides. So now I have y star minus alpha 1 y star equals alpha naught. Again, I'm going to factor out y star. So I get y star times 1 minus alpha 1 equals alpha naught. I divide both sides by 1 minus alpha 1, and that gives me my equation 1 here. Y star equals alpha naught divided by 1 minus alpha 1. And this is the general solution for finding a fixed point of the form. Good to know. So now that we know how to solve for this analytically, and we know what some of the rules are when it comes to the analytical solutions, let's look at this stuff graphically. So say we've got a function of xt plus 1 equals alpha naught plus alpha 1 xt. Well, really, it's no different than the yt equals alpha naught plus alpha 1 yt minus 1, because, well, all I did was just change the subscripts and change the variable, but the subscripts are off by just 1, right? T plus 1 and t, or t and t minus 1. So the difference between the time periods is still the same. It's just indexed at a different point. So it's really not all that different. But now we want to look at this at a graph, or in a graph, on a graph, whatever. How do we graph this? Generally, what you want to do is you want to put the dependent variable, the left-hand side variable, on the vertical axis, and the independent variable on the horizontal axis, or the right-hand side variable. So we're going to put xt plus 1 on the vertical axis and xt on the horizontal axis. So it's going to look something like this, right? Regular graph. Nothing too fancy about this. Okay. Now let's graph this function. Let's say we're going to graph that xt plus 1 equals 3 plus 1 half xt. All right, graph that. Cool. Intercept is 3. 1 half is the slope. So there we go. That's just the function. Now we want to solve this, right? We want to find what that fixed point is. Now to do that, we set xt plus 1 equals xt equals x star, as per the usual, as we've done almost ad nauseum thus far. When that happens, we just now really just need to know how to graph this. So how are we going to graph it? Well, when xt plus 1 equals xt for all t, what that means is if xt plus 1 equals 1, then xt also equals 1. If xt plus 1 is equal to 2, xt is also equal to 2. Do you see what's going on? As I do. It's giving us a 45-degree line that goes through the origin, which looks like this. So anywhere that xt plus 1 is equal to xt, well, 1 equals 1, 2 equals 2, 3 equals 3, 4 equals 4, so on and so forth. You're just getting this diagonal line. So when I set xt plus 1 equals xt equals x star, what we're doing is we're finding the point where that line xt plus 1 equals alpha naught plus alpha 1 xt crosses that diagonal line. If alpha naught is greater than 0, and the absolute value of alpha 1 is less than 1, then that fixed point's guaranteed to exist in the space where xt and xt plus 1 are both positive. So it makes no sense if you have like negative time values, right? Hence why these rules exist. Thus, when we set them equal to each other, what we get is x star equals 6, because that is the point where xt plus 1 equals 3 plus 1 half xt crosses that 45-degree line. So that 45-degree line, as long as the dynamical system will cross that 45-degree line, the point of intersection is the fixed point, or the steady state, or the dynamic equilibrium. So I'm going to solve this out again, iterate it a bunch of times. Xt plus 1 equals 3 plus 1 half xt. Suppose we start at xt equals 3 and we iterate until we get to that fixed point. Well, we would start with xt plus 1 equals 3 plus 1 half times 3. Evaluate that out. Comes out to 9 over 2, or 4.5. Now I take that 9 over 2 and I plug it back in. Xt plus 2 gives me 3 plus 1 half times 9 over 2, or 3 plus 9 over 4 gives me 21 over 4, or 5.25. Plug that in again, and I get 5.625. Now on a graph, what's happening is if you were to graph this out, if xt equals 3, this is your starting point, you go all the way up to this dynamical system, this function, and then you shoot over to that 45-degree line, and then up, all right? And here is that, what was it? I think 5.5? What was it? Yeah, 5.25, right here. That's 5.25. Okay. And then you evaluate it again, you get 5.625. And it's like staircases, like a zigzaggy, staircasey sort of shape up until you get to x star equals 6. Now, if you evaluate this over and over and over and over and over, it's going to converge to 6. It doesn't mean that you'll touch 6. You'll never actually get to 6. You'll get infinitesimally close to 6, but you won't actually get to 6. So I would say try it out on your own, starting with xt equals 10. Now, if you get stumped on xt equals 10, it's actually in the previous lecture, so you'll kind of see that zigzagging downward rather than upward, but it's still going to go to 6. So if you start above or below x star equals 6, you will zigzag your way back to x star equals 6. And in dynamic macro, this is like an absolutely, totally, incredibly fundamental, super important fundamental concept, because it's telling us if a system's at rest over time, then deviations from that system's point at rest will bring us back to where it was before this quote-unquote shock. And it ensures stability in the economic system over time as well. Now, you're probably like really confused, going like, what the hell is this guy talking about? You will see when we get to the solo growth model and then the neoclassical growth model, when we're analyzing steady states and deviations from steady state and return back to the steady state, namely when it comes to things like capital investment. But that's for another day and another chapter and another week. So this wraps up chapter 2. And we learned a lot. We learned about fixed points in dynamical systems, what happens if you change the parameters a little bit, the requirements to get a fixed point, and the graphs hopefully just further solidified what you saw analytically. Now, next we're going to be starting economic growth and development, which is where we're really just going to be using a lot of what we learned here, only applied to various economic models rather than just doing math for the sake of doing math. But that is the next lecture. Thank you for watching this lecture, and there will be more coming. So